Hi everybody, Queeveen here from the comfort of my kitchen. In today's video, we are going to take a look at the sun. So in one way, wintertime may be one of the worst times to observe the sun because it is so low in the sky. It's not up for very long and it's more likely to be blocked by trees or buildings. In another way, a wintertime may be a good time to observe the sun. As I've said before, and I will no doubt say again, never ever look directly at the sun. Never observe the sun directly. There needs to be some kind of protection involved. Pointing a normal telescope at the sun is risky not just for your eyes, but for the telescope due to the amount of heat that can be generated by focusing the sun's light. There needs to be some sort of special equipment involved, whether that's eclipse glasses or a special solar telescope that's designed for looking at the sun. We're taking a look at the sun here in wintertime, so of course it's lower in the sky and that means it's shining through more atmosphere, which is going to cut out even more of the heat and the dangerous radiation coming from the sun. It's going to attenuate the light, but not enough. You will need more help cutting down on the light from the sun and making it safe to observe. We can see a couple of sunspots here already, just taking a look at the sun. These sunspots aren't reflective of the sunspots that are currently on the sun. If we move through time here, we can see different sunspots coming into view due to the rotation of the sun. And because we're able to see different parts of the sun's atmosphere or surface, it's a little bit tricky with the sun, given that we're able to see different parts of the sun's disk here, the disk-like presentation that the sphere gives us, that's indicating that the sun's rotation isn't the same speed as ours. Every 24 hours that we turn around, the sun has turned around a different amount, a little bit more, as we can see here. By going forward every day, each bit of the surface seems to be drifting in one direction. If we take a look over at the side here, most planets do give a rotational period, but I don't know if the sun will, because different parts of the sun rotate at different speeds. The speed of rotation around the equator is different to the poles, and this is because the sun is a giant ball of plasma. We're going to get rid of the atmosphere here, which gives us a much better view of the sun. We can see lots more features of the sun here. And as we move through time, we can see changes in where the sun's pole is pointing at a given date by this kind of wiggling of the sun's magnetic field. We can see different features visible around the edges of the corona, but they're fixed. So this brings me back to the fact that the sunspots that we're seeing here aren't reflective of the sunspots that we're seeing currently. Because the sun is this giant ball of plasma, this magnetized ball of plasma, all of its surface features are shifting and changing around. Sunspots pop up and die away, and these lines that we're seeing here, the lines of the corona, they shift over time as well. These brighter lower down spots, which may be solar flares or coronal mass ejections, they're also going to shift and change over time, and as the sun rotates, these features are tied to its surface. Although we're seeing it as this surrounding corona, the corona wraps around the entire sun, so some of it is between us and the bright surface of the sun that we're seeing here, this illuminated ball. So these features of the sun would move with its rotation, disappearing on one limb and reappearing on another as the sun turns around. You can probably see it here even at this level of resolution. If we zoom in a little bit more, it may be more obvious, but the sun has this kind of dotted appearance. You might say it's granular. It's got all of these slightly different colored zones or regions on it. This is called granular, even though, as I say, the sun is a giant ball of plasma, and plasma behaves a little bit like a gas or a liquid. It's fluid, it moves around. And in the case of plasma, and in the case of the plasma in stars and on the sun in particular, it's strongly affected by the magnetic field that's going on around it. The ionized plasma, because the electrons are free, they're guided and moved around by the magnetic field. Deep inside the sun, everything's under so much pressure that the plasma is not as mobile. It's a bit more compacted together, and light and heat travel straight out. They radiate from the sun's core, where a lot of the fusion is actually happening. Here on the outside, where the plasma is under a bit less pressure, it acts a bit more fluid and convects, just like the convection currents you'd find in hot water, in boiling water, and in the Earth's magma, the Earth's core and mantle. There are convection currents where a hot central plume rises up and cools, and cooler edge plumes fall away. These cells, these convection cells, are what give the sun this granular appearance. Each of these, and again, this is pretty terrible quality, but each of these differently colored regions would be individual convection cells that are, like boiling water, moving around, convecting, twisting, sliding past each other and dying away as new ones pop up. It is a very dynamic system. Thanks to the sun's magnetic field controlling these convection areas, the magnetic field does tend to form these lines, these paths of magnetism that flow out of the sun and around and back around the top, as magnetic fields do. But these magnetic fields, they also vary in strength. The magnetic flux tubes, the columns of magnetism that rise up through the sun, sometimes they may have stronger intensity or lesser intensity, and this can affect the local temperature of the sun. So that does give us these sunspots that we see here, but they start as solar pores, smaller areas where the magnetic flux has changed and it causes a lower temperature. So these sunspots are thousands of degrees. They're up in the 3,000s of degrees, whereas a lot of the surrounding material would be up in the 5 to 6,000 degrees Kelvin. So 5 or 6,000 degrees Kelvin is around the temperature of stars like our sun, and then these cooler regions drop down to 3 to 4,000 degrees Kelvin, which is really hot. It's glowing red hot. It's as hot as the surface of many red stars, and you can head back to our recent video on stellar classification if you'd like to know more about the colors and the temperatures and how we talk about them. Our sun is a G-type star. I don't know if that's going to be written anywhere on the side, but that's part to do with its color, this kind of yellowy color, and its temperature. Sunspots are a lower temperature, and around sunspots we tend to see, and we can kind of see it here, the sunspots themselves are quite dark. The central region is the umbra, and solar pores are really just umbra, but they tend to grow or collect together and get surrounded by this region known as the penumbra. So the umbra is vertical magnetic field lines, whereas the penumbra has magnetic field lines that are a little bit tilted or skewed to the side. And this disturbance in the magnetic field, it gives birth to a lot of solar weather. When magnetic field lines that are pointing in slightly different directions, we can see the penumbra even better here on this big sunspot. The bigger the sunspots, the more penumbra they tend to have, and we often have sunspots where multiple spots are joined by one penumbra if the spots occur close together. And these penumbral regions with the magnetic field lines twisting around can lead to reconnection, where two magnetic field lines that would be moving in different directions instead sort of join up. If you have two loops, one moving one way and one moving the other, they may cut across each other and form two new loops moving in slightly different directions. And it's these changes at these magnetic reconnection events that generate or let out a lot of the energy that we see as solar flares and possibly coronal mass ejections. Coronal mass ejections aren't the best understood thing, but they are thought to be connected to magnetic reconnection. We can see the magnetic field, or the corona of the sun, which is high energy particles kind of trapped in this magnetic field. That's part of what gives it this kind of a stripy shape here. But again, the corona, what we're seeing rising out of the north and south poles here, some of these lines are curving down around in front of the sun, stretching out just as much as these ones here on the side, but we don't see them thanks to the light of the sun coming from behind. The sun is so bright that it makes the sunspots look dark, even though they would be glowing red, as bright as the moon for large ones, if they weren't surrounded by this much brighter sun, which makes them appear dark. When magnetic field lines reconnect, energy that's been stored up in these field lines, these kind of loops and things that we're seeing here are material, coronal material traveling along field lines. Loops that have built up energy can release this energy when the field line goes through reconnection. And that release of energy, it takes energy that the sun's been storing up for, a while, minutes, hours, and it releases it almost in an instant or in seconds. And this change in energy, this release of energy, is really what gives us solar flares and possibly coronal mass ejections. So the more sunspots we see, the more solar flares and coronal mass ejections that we're going to see. And it's when these sunspots are almost turned around facing us that the coronal mass ejection is going to come in our direction. If we see solar flares and ejections around the sides, the disk of the sun, they're pointing away from us. And even as the sun turns and even as they come through space, they're not very likely to hit us. It's only when they're almost facing us. Because they travel through space so quickly, they hit us pretty soon after they erupt. But by looking at the sunspots and the magnetic field activity around these sunspots, that gives us a good idea of when flares are going to be happening. So this ties in to all of the aurorae that people have been seeing lately. The sun is quite active at the moment. It's got a lot of sunspots, it's got a lot of these magnetic reconnection events, and that's creating the solar flares that are then coming through space, hitting our magnetic field, and creating the aurorae that we see. So even though it's very hard to predict solar flares, it's very hard to predict sunspots, we are able to observe them, and thankfully we know how they're related, and we can use that to give us a better clue as to what's going to happen in the future. So I hope that you enjoyed this video. I hope you enjoyed this look at the sun and discussion of why it looks the way it looks and these different features of it. If you did enjoy this video, then please do like it. If you like this kind of content, then please subscribe to this YouTube channel. And if you'd like to read some of this information, you can do so on my website, queevinscontent.ie. Thank you very much for watching, and hopefully I'll see you back here next time.